December 16, 1944. The Ardennes Forest, Belgium. German artillery observer Lieutenant Klaus Ritter crouches in a snow-covered foxhole, watching American positions through his binoculars. He's been on the Eastern Front, survived Kursk, knows what modern artillery can do. But what he's about to witness will violate every assumption he's ever made about how explosives work. American shells are falling on German infantry advancing through the forest 200 yards ahead of his position. Standard stuff. Except these shells aren't behaving normally. They're not hitting the ground and throwing up geysers of frozen earth. They're exploding in the air, 70 feet up, maybe 80. Perfectly timed airbursts that shred everything below them. Trees, men, equipment. The blast waves cascade downward with nowhere for soldiers to hide. Foxholes offer zero protection. Ritter watches an entire company, 200 men, get decimated in under 3 minutes. This deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. He's seen airbursts before, timed fuses that detonate shells at predetermined altitudes. But those require precise calculation of range, ballistics, and timing. Artillery crews spend years mastering the mathematics, and even then, maybe 1 in 5 shells bursts at the correct height. The rest explode too high, too low, or on impact. What Ritter is witnessing has a success rate that seems impossible. Every single shell. Perfect airburst, perfect height, perfect lethality. The Americans have deployed something new, something the Wehrmacht has no defense against. And in the frozen hell of the Battle of the Bulge, German soldiers are about to learn that their enemy possesses technology that shouldn't exist. Technology so secret that even now, 80 years later, the full story of its development remains partially classified. They called it the VT, Fuze. Variable time. Though the name was deliberately misleading, it had nothing to do with time. To understand why the VT Fuze represented such a revolutionary leap, you need to understand what came before. Artillery fuses in World War II came in 2 basic types. Impact fuses that detonated when the shell hit something solid. Ground, a building, a tank. These were reliable but limited. If you wanted to kill infantry in trenches or behind cover, impact fuses were nearly useless. The explosion happened at ground level, where terrain and fortifications absorbed most of the blast. The second type, time fuses, were supposed to solve this problem. Artillery crews would calculate the distance to target, factor in the muzzle velocity and trajectory arc, then set a mechanical timer on the fuse before loading the shell. The timer would burn down during flight and theoretically detonate the shell at the desired altitude over the target. In practice, time fuses were maddeningly unreliable. Calculate the range wrong by 50 yards, and your airburst happens over empty ground or doesn't happen at all. Wind, temperature, even the wear on the gun barrel, affected the shell's flight time. Experienced artillery officers could achieve maybe 15 to 20% accuracy, with time fuses under ideal conditions. In combat, with rapidly changing targets and incomplete range data, the success rate dropped to 10% or less. Most artillerymen just used impact fuses, because at least those were predictable. The United States Navy faced a different but related problem: anti-aircraft fire. Japanese aircraft attacking American ships in the Pacific forced gunners to try hitting fast-moving targets at altitudes between 5,000 and 15,000 feet. The mathematical challenge was staggering. You're not shooting at where the aircraft is. You're shooting at where it will be 4 or 5 seconds from now when your shell reaches that altitude. Naval 5-inch guns fired, shells that took 6 seconds to reach 10,000 feet. In those 6 seconds, a Japanese Zero traveling at 300 miles per hour covers half a mile. Your targeting solution requires perfect data on the aircraft's speed, altitude, heading, and rate of turn. Then you set a time fuse to detonate at the exact moment your shell and the target occupy the same point in 3-dimensional space. It was like throwing a baseball at a bullet and expecting them to collide mid-air. Pre-war US Navy estimates suggested that shooting down an attacking aircraft required an average of 2,500 shells. 2,500 rounds to kill one plane. Those numbers were catastrophic. A Japanese strike force of 50 aircraft could overwhelm any ship's defences simply by forcing the defenders to run out of ammunition. The problem wasn't the guns. American 5-inch 38 caliber naval guns were excellent weapons. The problem was the fuses. In 1940, before Pearl Harbor, the National Defense Research Committee began exploring radical alternatives. Dr. Merle Tuve, a physicist at the Carnegie Institution in Washington, headed Section T, the group responsible for fuse development. Tuve understood that mechanical time fuses had reached their theoretical limits. What they needed was a fuse that could sense its proximity to the target and detonate automatically at the optimal distance, a proximity fuse. The concept wasn't entirely new. British researchers had explored photoelectric fuses that detected changes in light when passing near a target. Those showed promise against ships, but were useless against aircraft at high altitude where light levels didn't change enough to trigger the sensor. German scientists had experimented with acoustic fuses that listened for engine noise. Those worked sometimes, but were easily confused by background noise and had very short effective ranges. Tuve's team at Section T took a different approach. Radio waves. What if you could build a miniature radio transmitter into the fuse itself? The transmitter would broadcast a continuous signal during flight. When the shell came close to something solid, an aircraft, the ground, a building, the radio waves would reflect back to the fuse. A receiver circuit would detect that reflected signal and trigger detonation. It was radar, essentially, built into a shell that would experience 20,000 times the force of gravity during firing and spin at 500 rotations per second during flight. The engineering challenges seemed insurmountable. You're trying to build a radio transmitter, receiver, amplifier, and battery power supply small enough to fit inside a 5-inch shell casing. The entire electronics package has to weigh less than 3 pounds and occupy a space smaller than a coffee can. Then you have to make it survive the shock of being fired from a gun, which creates acceleration forces that would pulverize any normal electronic device. And it has, to work reliably the first time, every time, because you get no second chances with artillery ammunition. The vacuum tubes were the first problem. Radio equipment in 1940 used glass vacuum tubes that were fragile even under normal conditions. The acceleration of artillery firing would shatter them instantly like light bulbs hit with a hammer. Tuve's engineers needed vacuum tubes that could survive 20,000 G-forces. For context, fighter pilots experienced maybe 6 or 7 GS during extreme maneuvers. Artillery shells experienced 20,000. The solution came from miniaturization and ruggedization. The team worked with tube manufacturers to design new tubes with reinforced glass envelopes, heavy-duty filaments, and shock-absorbing internal structures. They tested prototypes by firing them in artillery shells at the Aberdeen Proving Ground in Maryland. Most exploded on firing. The ones that survived got studied, improved, and tested again. By mid-1941, they had vacuum tubes that could reliably survive the gun launch. Power supply was the next nightmare. The fuse needed electricity to run its radio circuits, but conventional batteries couldn't handle the shock and spin. The team developed a spin-activated battery using reserve electrolyte technology. During storage, the battery was inert, just dry chemicals separated from the liquid electrolyte. When the shell was fired, centrifugal force pushed the electrolyte into the dry cells, activating the battery. Once activated, it provided power for the approximately 30 seconds the shell would be in flight. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The radio circuitry itself required innovations in miniaturization that preceded the transistor by nearly a decade. Engineers hand-assembled components on circuit boards barely 2 inches square. Every connection had to be shock-resistant. Every component had to tolerate extreme rotational forces. The transmitter operated at around 180 MHz, broadcasting a signal that reflected off objects within about 30 to 70 feet of the shell. When the receiver detected reflected signals above a certain threshold, it triggered a detonation circuit that fired the shell's main explosive charge. The entire sequence from detection to detonation took less than 1 millisecond. By late 1941, Section T had working prototypes. They weren't perfect, but they worked. A 5-inch shell fitted with a VT fuse would fly toward a target, sense when it came within detonation range, and explode automatically. No calculations, no range finding, no manual timer settings. Just point and shoot, and the fuse handled the rest. The first combat test happened in January 1943. The cruiser USS Helena fired VT-fused ammunition at Japanese aircraft attacking near Guadalcanal. The results were immediate and dramatic. Helena's gunners shot down 5 Japanese planes in a single engagement, using a fraction of the ammunition they would have been needed with conventional fuses. The gun crews didn't fully understand what made the new fuses so effective. They just knew the shells were exploding in exactly the right place at exactly the right time. Word spread quickly through the Pacific Fleet. Ships equipped with VT fuses were achieving kill rates 3 to 5 times higher than ships using conventional ammunition. The statistical difference was undeniable. Average rounds required to shoot down an attacking aircraft dropped from 2,500 with time fuses to under 100 with VT fuses. Some engagements saw single-shell kills, 1 round fired, 1 aircraft destroyed, which had been almost unheard of before. The US Navy implemented absolute secrecy protocols around the VT fuse. Crews were forbidden from discussing the technology. Spent shell casings had to be recovered whenever possible to prevent the Japanese from examining them. Most critically, VT fuses could only be used over water, where duds would sink and be unrecoverable. The Navy's greatest fear was that a VT-fused shell would land intact in enemy territory, allowing Axis scientists to reverse engineer the technology. This security concern meant the fuse remained exclusively a naval weapon throughout 1943. Army artillery officers heard rumors about miracle fuses that made every shot an airburst, but they weren't allowed to use them. Too much risk of leaving evidence on the battlefield. That policy held until the winter of 1944, when the situation in Europe became desperate enough to justify the risk. December 16, 1944. The same day, Lieutenant Ritter watched German infantry get shredded by airbursts in the Ardennes. Adolf Hitler had launched Operation Wacht am Rhein, the last major German offensive in the West. 21 divisions, over 200,000 men, supported by hundreds of tanks, smashed into a thinly defended section of the American line in Belgium. The goal was ambitious, almost delusional. Drive west to Antwerp, split the Allied armies, force a negotiated peace before the Soviets reached Berlin. The initial assault achieved complete surprise. American units were overrun, entire regiments surrounded, communication lines severed. Within 48 hours, German armoured spearheads had penetrated 40 miles into Allied territory, creating a bulge in the front lines that gave the battle its name. Bastogne, a critical road junction, became surrounded by German forces. The US Army's situation looked increasingly desperate. General Dwight Eisenhower, Supreme Allied Commander, made a critical decision. He authorized the use of VT fuses in ground combat for the first time. The security risk was real. German troops would inevitably capture intact fuses from duds or examine shell fragments, but the tactical situation overrode security concerns. American artillery batteries received emergency shipments of VT-fused ammunition with instructions, stamped in red across every crate, restricted use, critical areas only. The first ground combat use of VT fuses happened on December 22 near Bastogne. American artillery battalions supporting the surrounded garrison began firing VT-fused shells at attacking German infantry. The results were unlike anything seen in ground combat before. Every shell detonated at optimal height, approximately 70 feet above the ground, creating a circular kill zone roughly 50 yards in diameter directly beneath the airburst. The blast effects were devastating. Unlike impact explosions, where terrain absorbed most of the energy, airbursts directed their full force downward. Steel fragmentation spread in an umbrella pattern, shredding anything not under hard cover. Trees offered no protection. The fragments came from above. Foxholes offered no protection. The blast wave and fragments came straight down into them. Soldiers caught in the open were killed instantly by fragments travelling at thousands of feet per second. German infantry tactics, refined through years of combat on the Eastern Front, emphasized dispersion and use of cover. When conventional artillery fire came down, troops would spread out, take cover behind terrain features, get into shell holes or trenches. This reduced casualties significantly, because most shells that hit the ground only created danger in a relatively small area directly around the impact point. But against airbursts, dispersion meant nothing. Cover meant nothing. You either had overhead protection, a building, a bunker, or you were exposed. The psychological impact was immediate and profound. German soldiers who'd survived years of combat on the Eastern Front, who'd endured the siege of Stalingrad, who'd faced Soviet artillery barrages at Kursk, reported that American airburst fire was the most terrifying thing they'd ever experienced. You couldn't hide from it. You couldn't see it coming. There was no warning. Just sudden, simultaneous explosions overhead followed by death raining down from the sky. Major Joachim Peiper, commanding a Kampfgruppe of the 1st SS Panzer Division, recorded in his after-action report that American artillery fire during the Ardennes offensive achieved casualty rates he'd never seen before. His unit, advancing through forested terrain near Malmedy, came under sustained VT-fused artillery fire on December 19th. In less than 20 minutes, his lead battalion took over 40% casualties. 40%. From artillery alone. Peiper, an experienced and ruthless SS officer, couldn't understand what was happening. His men were dispersed properly. They were using available cover. They were following doctrine. But the American shells were exploding perfectly above them, turning the forest into a killing zone where trees provided zero protection. He ordered his advance to halt and requested smoke screens and indirect routes to avoid the artillery fire. The momentum of his attack, which had been driving deep into American lines, stalled completely. The Germans initially assumed the Americans had perfected time fuzzes to an impossible degree. Some officers theorized that American artillery crews had calculation tables and mechanical computing devices that allowed precise airburst timing. Others suspected radio-controlled detonation, imagining that observers were somehow triggering the shells remotely at the optimal moment. The truth, that each shell carried its own miniaturized radar system, was beyond their technological imagination. German intelligence did capture some VT-fused shells relatively intact, duds that failed to detonate, or shells that had expended their charges but left the fuse mechanism recognizable. These were rushed to laboratories in Germany for analysis. What the scientists found was both impressive and deeply disturbing. The Americans had built functional radio transceivers small enough to fit inside artillery shells. The level of miniaturization, the ruggedization required to survive firing, the reliability of the circuits, all of it represented manufacturing and engineering capabilities Germany couldn't match. The vacuum tubes alone were a mystery. German radio tubes were large, fragile devices used in tabletop equipment. The American tubes in the VT fuses were tiny, hardened, and incredibly reliable, despite being subjected to forces that should have destroyed them. The battery technology was equally advanced. Germany had nothing comparable to the spin-activated reserve battery system. Even if German scientists fully understood how the VT fuse worked, they lacked the industrial capacity to replicate it. By late 1944, German manufacturing was collapsing under Allied bombing. Factories were dispersed, raw materials were scarce, and skilled labour had been drafted into combat units. Building precision electronics on the scale required for mass production of proximity fuzzes was simply impossible. The Luftwaffe examined the technology with particular interest, recognizing its potential for anti-aircraft use. German cities were being pulverized by Allied bomber streams flying at 20,000 feet. A reliable proximity fuse could dramatically improve the effectiveness of German anti-aircraft defenses. But even understanding the principle didn't help. You can't build what you don't have the industrial base to manufacture. Germany in late 1944 was short on everything. Copper for wiring, high-grade materials for vacuum tubes, precision manufacturing capacity, stable electrical power for production facilities. The VT fuse wasn't just a technological advantage. It was a demonstration of American industrial supremacy. The ground combat experience of facing VT-fused artillery was viscerally different from anything soldiers had encountered before. Obergefreiter Hans Schmidt, an infantryman in the 326th Volksgrenadier Division, survived an American VT fuse barrage near Bastogne on December 24, 1944. His account, recorded during post-war interviews, provides a ground-level perspective of what the technology meant in human terms. Schmidt's company was advancing through open farmland south of Bastogne at dawn. Standard infantry tactics. Squads spread out, maintaining 15-yard intervals. When artillery fire was spotted, the drill was automatic. Hit the ground, find cover, wait for the barrage to pass. Impact explosions created danger zones, but if you were flat on the ground 30 or 40 yards from an impact point, you'd probably survive. The American barrage started without warning. No preliminary ranging shots, just sudden, simultaneous explosions overhead. Schmidt described it as like being underneath a ceiling that suddenly turned into fire and steel. The first salvo killed 11 men in his company before anyone understood what was happening. Soldiers who'd thrown themselves flat on the frozen ground were hit from above. The fragments came down at steep angles, penetrating helmets, piercing backs, shredding exposed flesh. Schmidt himself survived because he'd been near a stone farmhouse wall when the barrage started. He pressed himself against the wall, which provided overhead cover from the airburst pattern. Around him, men who'd followed standard doctrine and gone to ground were being killed in positions that should have been relatively safe. The psychological impact was immediate. Training and experience told you to get low, but getting low didn't help. The explosions were happening 70 feet up, and the killing radius extended straight down. The barrage lasted 8 minutes. When it stopped, Schmidt's company had taken 63 casualties out of 120 men, 52%, more than half the unit killed or wounded by artillery fire in 8 minutes. The survivors were in shock, not from the casualties themselves. Combat veterans understood losses, but from the complete ineffectiveness of everything they'd been taught about artillery survival. Schmidt's lieutenant, a veteran of the Eastern Front, immediately ordered a withdrawal. He recognized they were facing something new, something doctrine hadn't prepared them for. His report to battalion headquarters stated clearly that advancing through open terrain under American artillery fire was now suicidal. The unit needed buildings, thick forest canopy, or armor overhead to have any chance of survival. Similar reports flooded up the German command chain throughout late December. Company commanders were reporting catastrophic casualties from American artillery. Battalion commanders were revising casualty estimates for artillery from the traditional 5 to 10% to 30% or higher. Division-level planning officers were realizing that American artillery had suddenly become far more lethal than German artillery, which still relied primarily on impact and manually timed fuses. The tactical implications cascaded through German operations. Infantry attacks slowed or stopped completely when American artillery responded. Units refused to cross open ground without armoured support or heavy smoke screens. The offensive momentum that Hitler had counted on was bleeding away, partially from fuel shortages and Allied air power, but significantly from artillery fire that killed at rates German troops couldn't sustain. General der Panzertruppen Hasso von Manteuffel, commanding 5th Panzer Army during the Ardennes offensive, later testified that American artillery effectiveness increased dramatically during the battle. His initial intelligence estimates had assumed roughly equal artillery capabilities on both sides. By December 25th, he was reporting to OB West, the German High Command in the West, that American artillery had achieved a significant qualitative advantage through some technological improvement he couldn't identify. Von Manteuffel wasn't alone in noticing the change. Across the Bulge, German commanders were independently reaching the same conclusion. American artillery had become deadlier. Attack plans that had assumed acceptable casualty rates from artillery fire were suddenly producing unsustainable losses. Units that had planned to advance through artillery barrages were being stopped cold. The VT Fuze's impact extended beyond direct casualties. German infantry operations depended on speed and aggression. The Blitzkrieg doctrine that had worked so effectively early in the war emphasized rapid movement, breakthrough attacks, and maintaining offensive momentum. But VT-fused artillery created kill zones that couldn't be rushed through. You either had overhead cover or you died. There was no third option. This forced German units into predictable patterns. They concentrated in buildings and forested areas where tree canopy might provide some protection. They avoided open ground even when it offered the best routes. They moved primarily at night when American artillery observation was limited. All of these adjustments slowed operations and made German movements easier to predict and counter. American artillery officers quickly learned to exploit these new patterns. If German units were concentrating in buildings, you targeted the buildings with impact fuses to destroy the structures, then followed up with VT fuses to kill troops fleeing into the open. If Germans were moving through forests, you used VT fuses set to detonate just above treetop height, turning the canopy into a fragmentation source that sent wood splinters and shell fragments down onto troops who thought they were protected. The Battle of the Bulge became a turning point not just strategically, but in terms of artillery doctrine. American forces had demonstrated that technology could transform a traditional weapon system into something far more lethal. The VT Fuse took artillery, which had been roughly comparable between armies for decades, and created asymmetric advantage. German artillery still worked the same way it had in 1939. American artillery had leaped a generation ahead. By January 1945, the Bulge had been eliminated. German forces were pushed back to their starting positions, having lost over 100,000 men, killed, wounded, or captured. The offensive had failed completely. Among the many factors that contributed to that failure, American artillery equipped with VT fuses ranked prominently. Post-war analysis by U.S. Army operations research teams estimated that VT-fused ammunition increased artillery effectiveness by a factor of 3 to 5 compared to conventional ammunition. While ground combat in Europe demonstrated the VT fuse's lethality against infantry, the Pacific theater showcased its original purpose with even more dramatic results. Anti-aircraft defense. By early 1945, Japan had fully committed to kamikaze tactics, suicidal attacks where pilots deliberately crashed explosive-laden aircraft into American ships. The kamikaze represented Japan's response to losing the war of industrial attrition. They didn't have enough trained pilots, enough modern aircraft, or enough fuel for conventional operations. But they had young men willing to die and obsolete aircraft that could carry a bomb to a target. The mathematics of kamikaze attacks were grim. A conventional aircraft attacking a ship might get shot down without hitting anything, but a kamikaze only needed to make contact. Even a damaged aircraft crashing into a ship's deck could cause catastrophic fires and casualties. Japanese planners calculated that kamikaze attacks achieved hit rates of around 15 to 20%, far higher than conventional bombing. American fleet defense doctrine relied on layered defenses. Combat air patrol fighters engaged kamikazes at long range. Anti-aircraft guns created a defensive barrage at medium range. Close in, weapons, 40mm and 20mm guns, provided last-ditch defense. But kamikazes were difficult targets. They came in low and fast, often through clouds or at dusk when visibility was poor. They took evasive action, making targeting solutions difficult. And they were psychologically terrifying. Watching aircraft deliberately fly into your ship was unlike any other combat experience. VT Fuzes transformed the medium-range anti-aircraft layer from moderately effective to devastatingly lethal. American ships equipped with VT-fused 5-inch ammunition could put up a barrage of airbursts that created walls of shrapnel kamikazes couldn't survive. Unlike time fuses that required precise calculation and often missed, VT fuses detonated automatically when they sensed proximity to an aircraft. You didn't need to predict where the target would be. You just needed to put shells in the general vicinity, and the fuses handled the rest. The Battle of Okinawa, April through June 1945, provided the ultimate test of VT fuse effectiveness against mass kamikaze attacks. Japan launched over 1,900 kamikaze sorties against the American invasion fleet, the largest sustained aerial suicide campaign in history. The attacks came in waves called kikusui, floating chrysanthemums, with hundreds of aircraft attacking simultaneously to overwhelm defenses. USS Laffey, a Sumner-class destroyer on radar picket duty, experienced the most intense kamikaze attack survived by any ship during the war. On April 16, 1945, Laffey came under attack by 22 kamikazes and bombers over an 80-minute period. The destroyer's 5-inch guns, firing VT-fused ammunition, shot down 9 aircraft. Her 40mm guns destroyed several more, but 6 kamikazes and 4 bombs hit the ship directly. Laffey survived, barely. Fires raged across her decks. Her rudder was jammed. 32 crew members were dead. 71 were wounded, but she stayed afloat and eventually limped back to port. Post-battle analysis credited VT fuses with preventing complete destruction. Without airbursts automatically detonating near attacking aircraft, the ship's defenses would have been far less effective, and additional kamikazes would likely have hit, sinking her. Fleet-wide statistics told the story more clearly. Ships equipped with VT-fused ammunition shot down kamikazes at roughly 3 times the rate of ships using only conventional fuses. The average number of 5-inch shells required to down an attacking aircraft dropped from over 1,200 with time fuses to under 300 with VT fuses. That difference translated directly into survival rates. More kamikazes destroyed before reaching ships meant fewer hits, fewer casualties, fewer vessels sunk or damaged. The US Navy fired over 1 million VT-fused shells during the Okinawa campaign. Japanese sources, including post-war interviews with surviving kamikaze planners, indicate they were completely unprepared for the lethality of American anti-aircraft fire. Japanese intelligence had noted improved American defenses, but attributed it to more guns and better-trained crews. They never identified the VT fuse as the key technological factor, kamikaze pilots reported. Those few who survived aborted missions, that American anti-aircraft fire seemed impossibly accurate. Shells exploded near their aircraft even when no direct hits occurred. The blast waves and shrapnel from near misses damaged aircraft severely enough to cause crashes or force aborts. The traditional tactic of flying through anti-aircraft fire, accepting some damage to reach the target, didn't work against VT-fused barrages. The shells were exploding too close, too consistently. By June 1945, Japanese kamikaze effectiveness had dropped significantly. Early in the Okinawa campaign, kamikazes achieved roughly 15% hit rates. By late May, that had fallen to around 6%. Part of this decline reflected American tactical improvements, better fighter coverage, improved radar warning systems, but a substantial part reflected VT fuse lethality. Kamikazes were being destroyed in larger numbers before reaching their targets. The technology's effectiveness created strategic effects beyond individual battles. Japan's kamikaze strategy was predicated on inflicting unsustainable casualties on the American fleet, forcing a negotiated peace by making the invasion of Japan too costly. But VT Fuzes had significantly reduced kamikaze effectiveness, which meant Japan's last desperate strategy was failing. American ships were still being hit and damaged, but at rates the US Navy could sustain while maintaining operational tempo. Admiral Raymond Spruance, commanding 5th Fleet during Okinawa, later stated that without VT Fuzes, kamikaze attacks would have inflicted casualties severe enough to possibly delay the invasion of Japan. The fleet would have needed time to repair damaged vessels, replace lost ships, and reconstitute crew strength. VT Fuzes kept those casualties within manageable levels, allowing operational plans to proceed on schedule. The atomic bombs that ended the war in August 1945 overshadowed nearly every other technological development of the conflict. But VT Fuzes had already contributed significantly to Japan's defeat. They'd made kamikaze tactics far less effective, protected the invasion fleet at Okinawa, and demonstrated American technological and industrial superiority in a way Japanese leadership couldn't ignore. Post-war interrogations of Japanese military officials revealed that American technological advantages, including radar, sonar, and particularly the VT Fuze, had convinced many officers that continuing the war was futile. Japan couldn't match American innovation, couldn't replicate the technology, and couldn't develop countermeasures. The gap was widening, not closing. That realization, combined with atomic weapons and Soviet entry into the war, made surrender the only rational choice. The VT Fuze's development represented more than just a clever weapons innovation. It demonstrated what industrial-scale research and development could achieve when properly funded and coordinated. Section T, the organization that developed the VT Fuze, employed over 1,000 scientists and engineers at its peak. They worked with manufacturing partners across the United States to solve production challenges and scale up from prototypes to mass production. By war's end, American industry had manufactured over 22 million VT Fuzes, 22 million miniaturized radar systems, each one a precision device built to survive artillery firing and function reliably in combat. The production achievement was as impressive as the technological innovation. Germany and Japan had talented scientists who understood radio theory and could have designed similar devices in laboratory conditions. But neither had the industrial capacity to mass-produce them under wartime conditions. This pointed to a broader truth about World War II that's sometimes overlooked. Technology mattered, but industrial capacity mattered more. The side that could manufacture advanced technology in quantity won. Germany developed jet aircraft, guided missiles, and advanced submarines, but they couldn't build enough to change the war's outcome. America developed hundreds of technologies and manufactured them in quantities that overwhelmed Axis forces. The VT Fuze exemplified this principle. It was sophisticated technology made war-winning through mass production. Every American artillery battalion in Europe carried VT-fused ammunition by early 1945. Every American warship in the Pacific fired VT-fused anti-aircraft rounds. The technology wasn't hoarded or rationed. It was produced in such volume that it became standard ammunition, fundamentally changing how American forces fought. Post-war analysis by both American and German military experts concluded that the VT Fuze ranked among the most significant technological developments of World War II, alongside radar, penicillin, and the atomic bomb. Its impact on casualty rates, tactical doctrine, and operational effectiveness was profound. More importantly, it had been developed in secret, deployed without warning, and used on a scale that prevented effective countermeasures. The Cold War saw VT Fuze technology evolve into increasingly sophisticated proximity fuses used in every modern military. Surface-to-air missiles use proximity fuses to detonate near aircraft without requiring direct hits. Artillery shells still use them, though modern versions employ digital processing and laser sensors rather than vacuum tube radio circuits. Anti-aircraft systems like the Patriot missile rely on proximity, fusing to maximize effectiveness against incoming threats. Modern military doctrine considers proximity-fused ammunition standard for any anti-aircraft or anti-personnel artillery role. The concept pioneered in Section T's laboratories during World War II has become fundamental to contemporary warfare. Every artillery officer learns proximity fuse theory. Every air defense system incorporates it. The technological leap made between 1940 and 1945 became the baseline for everything that followed. The German soldiers who faced VT-fused artillery in the Ardennes, the Japanese Kamikaze pilots who flew into VT-fused anti-aircraft barrages at Okinawa, they experienced the leading edge of a technological revolution they couldn't fully understand. To them, it seemed like American shells had developed uncanny accuracy, almost supernatural precision. The reality was more mundane but equally impressive. American scientists and engineers had miniaturized radar technology, ruggedized it to survive artillery firing, manufactured it by the millions, and deployed it as standard ammunition. Lieutenant Klaus Ritter, the German artillery observer who watched his infantry get shredded by airbursts in December 1944, survived the war and was interviewed by American military historians in 1947. He described the VT fuse attacks as the moment he understood Germany had lost not just the battle, but the technological war. The Americans weren't just better supplied or more numerous. They possessed capabilities Germany couldn't match. Ritter had fought on the Eastern Front, survived Kursk, experienced Soviet artillery barrages that were massive in scale but used conventional ammunition. He understood artillery. What he witnessed in the Ardennes violated his understanding of what artillery could do. Every shell exploding at optimal height, no duds. No shells wasted by detonating too high or too low. Just perfect, mechanical, relentless precision. It was, in his words, like fighting enemies who could see in the dark while you stumbled blind. The VT proximity fuse didn't win World War II by itself. No single weapon or technology did. But it contributed materially to victory in both Europe and the Pacific. It saved American lives by making defensive fire more effective. It killed Axis soldiers and destroyed Axis aircraft with unprecedented efficiency. And it demonstrated that American industrial and scientific capacity had achieved advantages enemies couldn't overcome. In the frozen forests of Belgium, German infantry learned that cover no longer protected them from artillery. In the skies over Okinawa, Japanese kamikaze pilots learned that American ships could destroy aircraft without direct hits. And in laboratories and manufacturing plants across the United States, scientists and workers proved that technology, properly developed and mass-produced, could change the fundamental nature of warfare. The shells that exploded 70 feet above the Ardennes Forest in December 1944 carried more than high explosives. They carried the future of military technology, a future where sensors and electronics would become as important as armor and firepower. The Germans never expected American VT Fuzes to detonate at optimal altitude automatically. They couldn't have expected it because they didn't understand that such technology existed or could be manufactured at scale. By the time they learned the truth, the war was already lost, and the technological gap had become unbridgeable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.